Hello, students, and welcome back to physics. Um, if you haven't already, be sure you go through to Google Classroom, do your warm ups, and get your attendance credit for today. Um, Yesterday, if you remember, we briefly talked about motion, right? We really didn't go into it, but I introduced the concept of motion to you guys. Remember what we said motion was? So motion is a phenomenon in which object changes position over time, okay? And we said motion was relative, and that motion of bodies was observed by attaching a frame of reference. We also said that motion had direction conventions, right? We said that an object in motion can either be described as positive or negative in respect to its reference point. It can be moving in either a positive or a negative direction. The next thing we're going to talk about, and this will be new for today, are scalar and vector quantities. And it's important that we know the difference between the two so that we know how to treat each one. Let's see. So a basic definition of a scalar quantity is it's a quantity that has magnitude or an amount but no direction. Okay, it has a magnitude but no direction. They're quantities that are fully described by magnitude or numerical value alone. Some examples of scalars are mass and volume. Right? Mass just has some numerical value to it, no direction, and so does volume. Okay, so it's something that's not traveling a certain way, but it just has some number assigned to it. The next is a vector quantity. Now these can get a little tricky, but the basic definition is it's a quantity that has a magnitude and a direction. So not only does it have some value assigned to it, it's also got a direction. And if you've seen Despicable Me, there's a little nod to that vector. Okay, so vectors often go in many different directions and can be used in combination with one another. They can either add together or subtract from one another, and they can be solved or interpreted graphically and analytically. For the purpose of this course, we're only going to look at it graphically. We're not going to do analytical vectors calculations because that starts going into trigonometry and it's just not required for a basics physics course. Maybe if this was AP or an honors course, we'd look at it, but we're going to describe it mostly graphically. Okay, so what is a vector? We touched on a little bit with a basic definition, but here's a little bit more. Like I said earlier, it's a quantity that requires a magnitude and a direction to completely describe. So in vectors, an arrow is used to represent it, and the length of the arrow represents the magnitude. Okay, the length of the arrow represents the magnitude. What does that look like? Okay, so there's an arrow, right? We could say that that represents a vector. All right, we can call it a velocity vector. We'll say it's 100 meters per second. And what else does it say? It says the length of the arrow represents the magnitude. Now, obviously, this is, there's got to be some scale applied. We're not going to get into that. But if I wanted to draw a velocity vector that was 50 meters per second to the same scale as that one, if the length represents the magnitude, it should be half the size, correct? All right, and that one would be 50 meters per second. Sorry, that's a little illegible. Pen's acting up a little bit, but those are examples of a vector, and they would be traveling north, or you can say upwards. So the length of the arrow represents the magnitude, and the arrow is represented, or a vector is represented by an arrow. So we'll get that out of the way. We'll keep talking about vectors. All right. Some examples of vectors are displacement, velocity, acceleration, force, and momentum. These are all topics we'll get into, some soon, others much later, but those are examples of vectors, and you'll see that when we get to them. We start describing displacement. That'll be the first thing we talk about after this lesson. Some examples of non-vectors or scalars are distance, speed, work, and energy. So let's talk about vector addition. When two or more vectors are added, the directions must be considered. Vectors may be added graphically or analytically. Graphical addition requires the use of rulers and protractors to make scale drawings of vectors tip to tail. Okay, we'll talk about what tip to tail means in the next slide. And it's less accurate. Okay, it's less accurate. Analytical addition is strictly mathematical method using trigonometric functions such as sine, cosine, and tangent to add the vectors together. Okay, so let's look at a vector addition graphically. So here we have two vectors. We have vector A, and we have vector B. See, A and B here. Okay, that's our givens. It asks us to redraw as tip to tail by moving one of the vectors to the tip of the other. So here's how you do the tip to tail method. If we have a vector A, okay, we'll start with A. We'll leave it. We'll redraw it to the same magnitude as the original. We'll draw the same magnitude. If you were to draw it half the size, the other vectors would have to follow suit. So just to keep it simple, we'll copy over A the exact size. Now, tip to tail, what does that mean? Well, the tip refers to the pointy part of the arrow, okay? These here are the tips of the arrow. And the tails are these ends here. They're these ends. Right, those are the tails. So if we want to go tip to tail, we take the tip of vector A and the tail of vector B, and we add them together. You see that? So we redraw A, and then we move vector B so that the tail of it is at the tip of A. And that's the tip to tail method. So then, by doing so, we create something known as a resultant vector. Okay, that's what this R is representing. This is the resultant vector. You take where you started from, which is the tail of A, go to the tip of B, and that's your resultant. The resultant vector, which is the vector sum of A plus B. The resultant always goes from the beginning, the tail of the first vector, to the end, or the tip of the last vector. Okay, so this is what's known as a resultant vector. So in other cases, you may be asked to So in other cases, you might be asked to add multiple vectors. Unlike the last example, here you see three vectors A, B, and C. And right here, between A and B, if y'all remember from geometry, is an angle that's represented by the Greek letter alpha, okay, the lowercase Greek letter alpha. It represents the angle between vector B and the horizontal axis, which just so happens to be along the same line as A. So what you want to do if you're adding multiple vectors together are redraw the vectors tip to tail. Okay, so we redraw them. Okay, first you start with vector A, then you draw vector B tip to tail to A, followed by vector C, which goes tip to tail to B. So you'll have all three of them added together, tip to tail method. One important thing to note is that this angle here along the horizontal axis in B, after you've did the tip to tail method, should be the same as this one, as the original. That means, or I guess I should say, that's important because that means the vector B is still going in the same direction. Because a vector is defined by its direction, not only its magnitude, but also its direction. So it must keep that same direction at all times. You'll notice that vector A, vector B, and vector C, after we've added them together, are still pointing the same direction, and they are the exact same size as they were originally because they have a magnitude, which is the size, and the direction, which is the way it's pointing. All right. So then, what do you do when you have all three vectors? You draw your resultant. Your resultant is A plus B plus C. And theta here, which is that Greek symbol right there, that's theta, is the direction of R. R is your resultant vector, and theta is the direction. Okay. So then, we've covered vector addition with two or more vectors. Now we need to cover vector subtraction. Okay, so to subtract vectors, you add a negative vector. So it's the same thing as adding, but you're adding a negative vector, and I'll show you what that means in a second. A negative vector has the same magnitude and the opposite direction. Let's see what that looks like. So here's A, vector A, and there's negative A. Okay, that's what that's going to look like. So we have a vector, and then if we want to demonstrate a negative vector, we would flip it, make it go the opposite direction, and we'll call it negative. And we want to note that A plus negative A, which is the same as A minus A, is equal to 0. They cancel out. They cancel one another out. All right. So let's see what vector subtraction looks like graphically. So here we're given that we're given vectors A and vector B, and we need to find the resultant of A minus B. All right, so we're subtracting here. We're subtracting A and B, and we're still going to use the tip to tail method, okay? So don't forget that. So we're going to redraw tip to tail as A plus minus B. Previously, before we were subtracting, A plus B would look like this, right? Well, what about A plus minus B? So we're subtracting B. So remember we said 2 slides ago that the last slide, a negative vector is going to have to point, has the same magnitude, but it's going to point the opposite direction. So what then does negative B look like? Well, there it is. That's negative B. So here we're saying A plus negative B. Up here, where my pointer's at, that's A plus B. This is A plus negative B. And in which case, B is going the opposite direction, but it has the same magnitude. Or this arrow here that's representing this vector is the same length as the original. And our resultant is going to be from the tail of the beginning vector to the tip of the ending vector. So here's a little note. In addition, vectors can be added in any order. In subtraction, you must consider the order so that the right vector is reversed when added. So in addition, it don't matter. You can start with A, B, C, D, E, F. It doesn't matter. You can start with either one of them and add them. But since you're flipping a vector here for subtraction, the order is important. Okay? It's important. And one way to think about it is if you go back through and rework this problem, but then you say, but then you flip A, you reverse A instead of B, you'll realize that you don't have the same resultant vector. And why is that? Well, because essentially, if you reverse A, you're saying negative A plus B, which is the same thing as B minus A. And that is not the same expression as this. Okay, that's not the same thing. So order matters. Remember the order when you're subtracting vectors. So the next thing we're going to talk about is an equilibrant. An equilibrant is a vector that okay, so an equilibrant is a vector that is the exact same size as the resultant would be, but the equilibrant points in exactly the opposite direction. Okay, so why is this important? What does it mean to be in equilibrium? Equilibrium is a state in which opposing forces or influences are balanced, or you can think of it as opposing vectors are balanced. Okay, so if we have two vectors A and B here, and we want to find the equilibrant, what do we need to do? We need to first redraw as tip to tail, right? Find the resultant, then draw an equivalent and an equal and opposite direction. An equal and opposite direction of the resultant is what it really should say. So let's see what that looks like here. Okay, so here we have A and B. We did our tip to tail method. We found the resultant by doing simple vector addition. And then, after we found the resultant, in the opposite direction, we drew a vector of equal magnitude. So what does that mean? So the equilibrant brings all of the vector sums to zero so that an object is in equilibrium, right? So an object is in equilibrium. When you're dealing with forces, it refers to mechanical equilibrium, meaning that everything's balanced and it's not basically it's not moving, right? Relative to where the forces are coming from, that is. So that's an equilibrant. Okay, so why do I need to know this? Or why do you need to know this? Particularly for this unit. I know I've used forces a lot and in my examples, but that's going to come into unit 2. So graphical analysis of vectors is useful because they can visually represent position, displacement, velocity, and acceleration. Right? Remember, those are our vector quantities that I talked about earlier. They can graphically represent position, displacement, velocity, and acceleration. So that's why we need to know that. So if we have multiple velocity vectors coming from different directions and you want to know the resultant, well, there you go. You can draw it out with graphical analysis of vectors.